f is a function of two variables x and y. The partial derivative of f with respect to x at the point with coordinates x0, y0 can be written like this: f sub x at x0, y0. Now I don't have a graph of the function z equals f of xy. That's going to be some surface, of course, but what we will consider is a cross section of the surface with the plane y equals y0. That's a plane that's parallel to the xz plane and points and passes through y0 on the y-axis. In particular, of course, it'll pass through the point with coordinates x0, y0. So we're interested in getting the slope of the surface at this point, but we want the slope of the surface in the x direction. So to do that, we consider a nearby point whose coordinates are x, y0. So this nearby point is also in the plane because its y value is y0. When we calculate this quotient here, we are getting the slope of a secant line passing through these 2 points. The vertical distance between these 2 points is given by f of x at y0, the value of the function at this point, minus the value of the function at the point with coordinates x0, y0. So that's the vertical distance between the points, and the horizontal distance between the points is the difference in the x values between these 2 points. Well, that's just x minus x0. So we've rise over run for the slope of this secant line. Now if we take the limit as x approaches x0, then what we are doing is moving this point towards this point. This point stays fixed, of course, so we move this point in this direction, and the secant becomes a tangent line at the point directly above x0, y0 on the surface. So here I'm showing the tangent line in red. Its slope at the point with coordinates x0, y0, its slope is the partial derivative of f with respect to x. So this red line is a line in this plane which is parallel to the xz plane. Now let's consider the partial derivative of f with respect to y at the point x0, y0. So we're dealing with the same point, x0, y0. Well, we want the partial derivative in the y direction, so we have to consider a point that's close to x0, y0. But we're only changing y, so we want the x value of this nearby point to be the same as the x value of this point. So the x value of this point here must also be x0, and the y value can be any number, but of course we try to make y close to y0. So the y value is this value here, and y0 this value here. Okay, we will be evaluating the function at both of these points. So we've gone up to the surface or down to the surface, depending. I'm not going to show the surface, but we want to get the function at both of these points, get the difference, and divide by the distance between the points, which is y minus y0. Then take the limit as y goes to y0, and we will have the derivative of f in the y direction. So imagine that this is a piece of a curve which is the intersection of the plane x equals x0 and the surface f of xy. So this is a piece of the cross section of that surface. So the slope of the secant line through these 2 points is given by this quotient here. So again, it's rise over run. The vertical distance between the points is the numerator here, just the value of the function at each of these points. Get the difference in those values to get this distance. It could be positive or negative. We're not too concerned about that. And the horizontal distance is just this distance along here, y minus y0. Again, it doesn't matter too much about the sign, but if we take the limit as y tends towards y0, keeping x0, y0 fixed, then this point will move towards the point that we're interested in. So this will move in this direction, and the secant line becomes a tangent line. So we'll end up getting the slope of the tangent to the surface at x0, y0. And we are talking now about a tangent that's entirely in the y direction. So we're dealing with the slope of the surface in the y direction at the point with coordinates x0, y0. Now, let's consider this mixed derivative. We saw that the meaning of this thing is given by, first of all, differentiating f with respect to x, then differentiating the result with respect to y. Now, in other books it's the other way around, but it doesn't actually matter, because we will see that for nearly all functions the order of differentiation is irrelevant. But let's apply the limit definition to this mixed derivative. So basically we're going to use this result here, but instead of applying it to the function f, we are going to apply it to the function f sub x, the derivative of f with respect to x. So we just put in the subscript x here. So that's all we did. We just wrote this out, replacing f with f sub x. Now we can go back up to this and look at the partial derivative of f with respect to x. So this function here looks very like this one, except that instead of y0 we have y. So we just copy this out, but y0 is just y. So we're going to get the limit as x tends towards x0 of function f at x comma y0, but instead of y0 we have y. So we have x comma y there, minus the function at x0 comma y0. In this case it's going to be x0 comma y, and that's divided by x minus x0. So you see we're keeping y fixed, although it's not y0 as it is here up here. It's just y, but x is changing. X is approaching x0. So we'll be getting the partial derivative of the function f at x0 y. That's exactly what we want. Next we want f sub x at x0 y0. So we just copy this down. Okay, so here is f sub yx at x0 y0. Now let's consider f sub xy at x0. To get this second partial derivative, we have to differentiate the function f sub y with respect to x. So to differentiate the function with respect to x, we have to take this limit here. But the difference is, in place of the function f in this limit, we have the function f sub y. So that's the only change we have. We just stick in the subscript y here, because we're differentiating f sub y with respect to x instead of differentiating f with respect to x. Next we need to apply the limit form for the partial derivative of f with respect to y. So we just follow this here. Basically we just plug this thing in for this term here. It's just identical to this. Now what about this term here? Well, we just plug this in, but the only difference is instead of x0 we have x. So there it is, and we can just copy this out here and just replace x0 with x. In previous videos we calculated these mixed derivatives for various functions. We saw that in general these two mixed derivatives are the same. In the next video we will prove that.